factors like nutrients, toxin, drugs, temperature, and humidity to then start building in vitro communities that can be used as tractable model systems to study complex microbiomes. And so this top-down approach has been used in multiple studies to try to understand fundamental ecological principles of microbial community assembly, and here I'm just showing you a few. But also, more recently, it has been used to build stool-derived in vitro communities to study gut microbiomes. And so this work was led by Andres Arrodillas and Tracy Gonzalez at Stanford. And so what Andres did was to take a stool from humanized mouse and then inoculate it into BHI medium, which is a rich medium, and let the communities grow for 48 hours. And then it comes back and dilutes the communities back into fresh media, and then repeats this growth dilution cycle multiple times. And at the end of each passage, the communities were frozen and then sent for sequencing. And so what Andres saw was that just after a few passages in BHI medium, the communities do very quickly transition to a diverse and stable state. And also, more importantly, is that these communities do resemble the in vivo community in the mouse. And so what this shows is that these stool-derived in vitro communities in BHI are a good model system to study gut microbiomes and also how they respond to perturbations. And so the gut environment faces a lot of perturbations from their external environment, but one I've been very interested in over the past few years is nutrients. And especially the question of how do gut bacterial communities respond to nutrient perturbations. And so to work on this, I collaborated with Andres, and so what we did was to collect samples from 8 human donors, and then passage them in complex media, so in BHI supernated with a single carbon source. And we used 22 different carbon sources, and here I'm just showing you the ones we use. They are highlighted in bold and also in color. And so they cover both sugars and acids, and they are diverse. And then we passage the communities 7 times into this medium, and then at the end we measured OD, which is a proxy for community yield, and we also did 16S-RNA sequencing to look at community composition. But the first question really we need to ask is, so what are the possible outcomes of carbon source supplementation? And so one of them is that there is no change in community composition. And so this could happen if, for instance, none of the species that are present can consume added carbon source. Or also it could happen if all of the species can equally benefit from that carbon source. So then in terms of relative balance, we would basically just see the same. Another outcome is the complete restructuring of a community where, for instance, species that are present in BHI, so in the complex medium, are very different from the ones that are present in the complex medium plus added carbon source. And another scenario is that a single species will have exclusive access to that added carbon source while the other species remain unchanged. And so what do we see? So what I'm showing you here is a takeaway of the unweighted unit distance of the communities, either colored by carbon source or by donor. And so what we can see is that using this metric that takes into account species absence and presence, then the communities do cluster by donor, but not by carbon source. And this is not really surprising because the metric that takes into account species presence and absence will be very biased towards the inoculum, because the different donors will carry different set of strains, and so if a strain is not present in the initial inoculum in the first place, then it will not make it into the mutual community. But then when we use a metric that takes into account relative imbalance, so when we use weighted unit frac, we see that the communities now do cluster by carbon carbon source, but not by donor, which suggests that the nutrients dictate their abundance. Then we zoom into the communities to look at what families are present. And so here what I'm showing you is on the x-axis the community biomass, so the OD, and then on the y-axis the abundance of one family. And each dot represents a different carbon source, and I'm also highlighting the BHI only scenario, so without any added carbon source. And what we can see is that this family, the Enterobacteriaceae, increase in abundance with community biomass. But when we look at other families, so for instance the Bacteroideaceae, they do remain at constant abundance regardless of the community biomass. And this trend also occurs for other families, and so for instance, we see that families that belong to the Lactobacillus do also increase in abundance, while most other families, and especially the ones that are at low abundance, do remain at constant abundance regardless of the carbon source that we are having. And so in the next slides, I will use the term enteros for the families that belong to the Enterobacteriaceae and also the ones to the Lactobacillus, because they can explain most of the increase in abundance with community biomass. And so far, what we have found is that across most carbon sources, it does seem that a single family or families belonging to enteros do have an exclusive access to that added carbon source, while most other families do not and remain unchanged. And so this raises two questions. So one is, so why do the enteros dominate across most carbon sources, and also then why do most families just remain constant abundance? And so the potential explanation for why the enteros dominate is that they are actually the only one who can use that carbon source, while the other families cannot. And so to test this idea, we used a collection of 15 strains that were isolated from a stable stool-derived in vitro community. And so these cover most major family and also close to 70% of the parental signal banks. And then we grew them alone, so in monoculture, in BHI plus each carbon source. And so what do we see? So here I'm showing you a heat map of the final OD for each strain in each given carbon source, and I'm also highlighting the BHI scenario. And what we can see is that most strains can actually grow on the supplemented carbon source, and also that in certain carbon sources, Bacteroides fragilis can even reach higher yield than the enteros. And so what this is suggesting is that it's not the ability to consume a carbon source that is dictating who dominates in the community, but rather it does seem to be the dynamics of nutrient utilization. So when we look at the dynamics, and what we can see is that indeed E. fergusoni, which is the dominant Enterobacteriaceae strain, grows early and fast, while Bacteroides fragilis grows later and also more slowly. And this is across all carbon sources. And also this pattern, we see the same in the other families. So the enteros tend to be early and fast growers, while the non-enteros tend to be late and slow growers, and across all carbon sources. And so what this suggests is that E. fergusoni, or more broadly the enteros, do deplete the supplementary carbon source before the slow growers can even start consuming it when we are in the context of the community, so when we are together. Also, what was interesting is that when we zoom into the initial growth of E. fergusoni, we can see that it is the same regardless of the supplementary carbon source, and also the same as in BHI only, so without any carbon source added. And so what this suggests is that there are actually two phases of growth. The happens in the context of the community. And so what we suggest is that the reason why the enteros dominate across most carbon sources is that they do have an early bird advantage by depleting their niche of the nutrients that they prefer in PHI first and early, and then they are the first one to be able to switch to consuming the added carbon source. But this doesn't still explain why do most families remain at constant lower bands across the different carbon sources. And so for this, we look at the species dynamics during a single passage in PHI, and we can see that the Enterobacteriaceae are the faster growers, followed by the Enterococci strains, but then the Bacteroideaceae and the Lachnospiraceae can still grow later, even when they are in the context of the community. And so what we suggest is that there is actually a resource petitioning in PHI, so in the complex medium, that allows the soil growers to persist even if they grow more slowly. And so the reason why they remain at constant balance might be because of this resource petitioning. So then the next question that we were interested in was, so can we actually predict the dominance of the fast growers in the communities from their growth in isolation alone? And so there are multiple ways to predict community composition from growth in isolation. So one is to take into account the ability to use carbon source, which is captured by final OD. The other one is to take into account the dynamics of carbon source utilization, which is captured by area under the curve. But also, another way is to take into account the dynamics of carbon source depletion. And so for this, we developed a matrix of time T, which basically represents the time of resource depletion in the community that we assume to occur when the OD of the community is equal to the sum of the OD of the isolates. And so then we develop a metric to determine each member's contribution to the excess community growth when the carbon source is added. And so here, this is the metric that we have, and then we parameterize this metric with each of the parameters. So either the final OD, AUC, final OD at time T star, or AUC at time T star. And then we test the model predictions with a 15-member community that is reconstituted from the 15 isolates. And so what do we see? So what I'm showing you here is the data for the 15-member community, so experimental data, and also the predictions of the model using final OD and AUC. And so what you can see is that the final OD and AUC do overestimate the abundance of the slow and late growers. But then when we use final OD at T star or AUC at T star, then we can see that we can much better make predictions. And this is not really surprising because the reason why we cannot predict so well the dominance of Enterobacteriaceae and Enterococci when we don't take into account this timing of nutrient utilization is because when the slow growers are alone, they can grow well on those carbon sources. But which is not a problem if they are alone, but then it becomes a problem when they are in a community with other species that can deplete the resources before they can even have access to those. So then the next question we were very interested in was, so can we actually predict community composition in a community that lacks the faster grower? And so when we look at, again, at the community composition of the parent stool-derived individual community in PHI, we can see that the faster is the Ephemeris strain, while the second fastest grower is the strain of Enterococcus. And so then our prediction would be, if we were to remove the faster grower, then maybe the second fastest grower would be the one takes into account the time of nutrient depletion better predicts community composition. While when we don't take into account that time of nutrient depletion, then we do overestimate the presence of the slow growers, so of the leptospiration and bacteridaceae. And so, what have we learned? So just to summarize what I've shown you today is that communities across most carbon sources are dominated by the same family, which increases the abundance of community biomass, while most other families remain at low abundance. And also that the reason why the enteros dominate is because of an early bird advantage where they deplete their niche first in the complex medium, so in DHI, and then they are able to be the first one to switch to consume the added carbon source. Also, I've shown you that most families do remain at constant low abundance across the different carbon sources because of resource partitioning in DHI, and also that we can predict community composition from a single species growth, but for that, taking into account the dynamics of resource consumption and also depletion is key to make successful predictions. Otherwise, we overestimate the abundance of the slow and late growers. And also, I've shown you that there is a line of succession for